Hello everyone, welcome to my class. Today we will hold last lecture of module 7. Now in this lecture we will talk about Fraunhofer diffraction pattern of multiple slit. In the lecture before we talked about diffraction pattern produced by single and double slit in Fraunhofer design. Today we will generalize these two slits. Now this is a schematic diagram of a multiple slit where you see that the slits are placed horizontally. This is contrary to the case where we discuss single and double slit, their slits were placed vertically, but the axis is unchanged. Now you see that since we have rotated the slit, therefore the axis also got rotated. Y axis is in the direction of length of the slit, x is coming out of the plane of these slits are plane of the aperture, and z axis is pointing upward vertically. Yeah, this is your z axis, this is your y axis, and this is your x axis. Okay. The point of observation P, similar to the previous cases, is very far from the slit, and the origin is placed at the center of the lowest slit, the lowermost slit. Okay, the origin O is here, and the distance of the point P from the origin is capital R. Okay, and this P is very far from the slit, therefore we have introduced these two parallel lines which represents break. Okay, it means that the this length OP is very much larger than the length which is shown here in this figure. Now there is since we are talking about mini slits or multiple slits, then we assume that they have there are n number of capital N number of such slits, and for any jth slit, suppose there is we pick some random slit and which we assign a number j. Okay, from jth slit the distance of point P is rj, and the line OP is at angle theta from x axis, while this rj makes an angle theta j from a plane. This plane is xz plane. Yeah, this is the shaded region is the xz plane, and with this plane this line which is of length rj is making an angle of theta j. Now these all slits are identical, and the slit width is small b, and center to center separation is a. Okay, this slit width and center to center separation a is same as what we studied in double slit experiment. Now we will again apply the same mathematics which we developed for single slit and then apply to double slit. Okay. In double slit we solve two integrations. Okay. Now since here the number of slits are capital N, we will solve n integrations. Okay. And these are the integrations. Okay. Here fz is your this function which we already derived in previous classes. Since the origin is at the center of the lowest slit, the limit of integration from the first integration will vary from minus b by 2 to plus b by 2 as shown in the figure. Similarly, for the second slit it would be a minus b by 2 to a plus b by 2. In case of double slit experiment, we just solved these two integrals. Here we just took into account these first two terms in double slit experiment. Now we are now in this case we have large number of slits. In this particular case we are considering capital N number of slits, therefore n such integrals would be written with appropriate limits. Yeah. Now for the third slit, the limit would be like this here, 2a minus b by 2 to 2a plus b by 2, and similarly for last slit the limit would be n minus 1 a minus b by 2 to n minus 1 a plus b by 2. Okay. Now we will have to solve all these integrals. Okay. Now out of all these integrals we will pick the integral for jth slit. Okay, we will solve this and then sum over j. since we are in Fraunhofer regime, therefore, Fraunhofer conditions apply here, and therefore, the aperture configuration must be such that all slits are close to origin and this approximation is valid, and we assume that this is applicable over the entire array of the slit. This we derived in case of single slit. Okay, this is the Fraunhofer condition. Now, with this we will solve the jth integral, and after integrating we get equation number 44. While solving this integral, we assume that theta j is equal to theta. Let us go back to the figure. Now, in this figure, theta j is this angle. Okay, this angle is theta j, while this angle is theta. Now, if you consider point P very far from the aperture, and this aperture plane where in a number of slits are there, this aperture are all these slits as compared to the distance between the slit and the point of observation would be very small. Therefore, we may assume that slits are so closely spaced that angle subtended by a line starting from center of each slit to the point of observation P subtend the same angle with xz plane, this plane. I repeat, since point of observation is very far and slits are very thin, the width is very small, even the center to center separation is also very small. Therefore, the line starting from center of each slit and reaching to point of observation P subtend an angle which is same irrespective of the slit numbering. Okay. And this angle is being subtended from a plane which have x and z axis. Okay. And this angle which we designate as theta j is equal to angle theta, which is the angle of point of observation P from origin with respect to x axis. Okay. With this approximation, we solve this jth integral, and after some manipulation we get equation number 45, which represents the contribution of electric field or contribution of disturbance at a point of observation P due to jth slit in n number of slits. Okay. Now, here you see a new term alpha. Okay. Now, alpha is Ka by 2 sin theta, okay, while beta is Kb by 2 sin theta. Okay. Beta is here in this sinc function. This we have already talked about in double slit experiment. Now, if you go to the phase part of equation number 45, then you see that we have sine function with omega t, and if you take minus out, then you will have this in the as a second term. Now, Kr minus 2 alpha j is the phase part in equation number 45. This is a time varying phase part, and this is spatial phase part, space dependent phase part. Okay. And it is Kr minus 2 alpha j. Let us talk about this. Now, Rj, which is the distance from the center of jth slit to the point of observation P, this would be equal to R minus Ja sin theta, okay, and which is very much clear from this figure also, okay, because center to center separation is A, and to calculate Rj, these are the slits, okay, and these slits are separated by distance A, okay, the adjacent slits are separated by distance A, and slit width is B, okay, which is very small. Now, the point of observation is P here. Now, suppose this is our jth slit, then this distance which we designate at Rj, this would be equal to, like, suppose this is your lowermost slit, then this would be capital R, and the part difference would be this much. This would be your optical part difference, okay, and this optical path difference would be equal to J, which is the number of the slit, into A sin theta. Okay. Therefore, Rj would be R minus J sin theta. Okay, this which is very much clear from this figure. Yeah. Now, with this we can write that minus K R plus 2 alpha j, this would be equal to minus K into R j, because alpha is K by 2 sin theta. Okay, with this substitution we get this relation. Now, minus K R plus 2 alpha j is equal to minus K R j. What is this? Let us go back. Now, you see here minus K R plus 2 alpha j is here. Okay. Therefore, we can equivalently write this as sin omega t and minus K into R j. This is what we get after the substitution. Now, this is the phase which the light accumulates in reaching to point P. Okay, the light starts from the center of jth slit and then it reaches to point P, and during this propagation the light accumulates a phase which is now equivalent to k dot r j, and which is now very much obvious, because minus k r plus 2 alpha j is equal to minus k r j, which is given by equation number 47. Therefore, this equation number 45 is now well understood. Okay, and the phase part is also understood. Why is it coming so? Now, once the field due to jth slit is calculated, then we have to just sum this field up over all the slit numbers. Okay, and this summation will give us the total field or total disturbance at the point of observation P, and therefore, once Ej is calculated, we sum over Ej, where j starts from 0 to n minus 1. Yeah, make it a point. The counting of the slits starts from 0. Okay, this is our slits, and we start counting the slit from 0. Yeah, j is equal to 0 here, then j is equal to 1 here, and so on, and at last j is equal to n minus 1. Okay, it ends at n minus 1. Since the counting starts with 0, therefore, the total number of slits in this case would be n. Okay. Now, let us perform the summation over the Ej, and the summation gives this. Okay. Now, you see that it is a sine function here. We can also express it in form of complex representation. In complex representation, the imaginary part of this expression will give us sine, yeah, because e to the power I theta is equal to cos theta plus I sin theta, and sine is coming with iota I. Therefore, imaginary part of this complex representation will give us back equation number 49, which has sine function. Now, this summation, which is sigma e to the power I to alpha whole to the power j, is already done. We did it when we were dealing with point oscillators in the very beginning of diffraction. Okay. We will borrow the knowledge of summation from there and directly write the results here. Then after summation and doing a bit of mathematics, we land up with this value, this expression of the total electric field at the point of observation P. Okay. Now, the distance from the center of the array to the point P would be equal to r minus n minus 1 a by 2 sin theta. This also have been done previously while dealing with this point oscillator. Now, this distance is visible here too, okay, in equation number 51. Okay. Therefore, ultimately we can calculate the flux density function, which is irradiance. Okay, once the total electric field expression is done, we can easily calculate the irradiance, and the irradiance is given by equation number 52. Now, you see that we have sink square function, which is symbolizes the diffraction produced by single slit, and then we have this function which is new, sin n alpha by alpha whole square. This function was neither there in single slit diffraction expression nor in double slit diffraction expression. Okay. While this function, this sink function sin beta by beta whole square were there both in single slit as well as in double slit expressions. Now, I naught is the flux density or irradiance in theta is equal to 0 direction emitted by any one of the slit. Okay. And therefore, if you substitute theta is equal to 0 in equation number 52, you get I 0 is equal to n square I naught. It means in 0 direction, in theta is equal to 0 direction, the resultant irradiance would be n square times I naught. I naught is contribution from the single slit. If you increase the number of slits, the total irradiance will increase by n square times into I naught. Now, as the expression 52 suggests, we will have single slit diffraction pattern also in the complex pattern produced by multiple slit. We will have single slit diffraction. Therefore, each slit by itself would generate precisely the same flux density distribution. Now, if the width of each aperture shrinks to 0, means if we start reducing the width of each slit, then flux density distribution would be similar to that of linear coherent array of oscillator. Okay. Why is it so? Because suppose these are the slits which we are talking about, and if you reduce the width to 0, then we will have a single line oscillator. Okay. Now, the principal maxima occurs when this function sin n alpha upon alpha is equal to capital N, and when does this happen? This happen when alpha assumes these values which are integral multiple of pi. Okay. For principal maxima, alpha must be integral multiple of pi, which is 0 plus minus pi plus minus 2 pi plus minus 3 pi. Or equivalently, what we can say is that since alpha is equal to k by 2 sin theta, then from this expression a sin theta m is equal to m lambda. This gives now the principal maxima where m is an integer, and the value of m is known as the order of diffraction. Okay. If m is equal to 0, it is a principal maxima, it will give you the intensity in the straight direction, while m is equal to plus 1 or minus 1 designates first order maxima. Similarly, m is equal to plus 2 or minus 2 designate second order maxima, and so on. Now, for minima of 0 flux density exists when this function is equal to 0, sin n alpha by alpha is equal to 0. Okay, and this appears when alpha is equal to plus minus pi by n or plus minus 2 pi by n, and so on. Now, between consecutive principal maxima there will be n minus 1 minima, and between each pair of minima there will have to be subsidiary maxima. How to decide the position of subsidiary maxima? The subsidiary maxima are located approximately at points where sin n alpha has its greatest value. And what are those alphas? Those alphas are given by this plus minus 3 pi by 2 n, plus minus 5 pi by 2 n, and so on. Therefore, n minus 2 subsidiary maxima can be seen between consecutive maxima. I repeat, between consecutive principal maxima there would be n minus 1 minima, and n minus 2 subsidiary maxima can be seen between consecutive maxima. Now, this becomes very clear when you plot equation number 52. Now, here the multiple slit pattern is shown, the diffraction pattern or irradiance pattern. Now, on the vertical axis I by I naught is plotted. When capital N or number of slit is equal to 2, then you see this dash line pattern, and when n is equal to 6, then you see this continuous pattern. Now, in this first figure, this whole pattern is not plotted. In this first figure, we picked only this part, and this part is plotted here on the vertical axis. Okay, and this is, you see here this function sin square n alpha upon sin square alpha. On the vertical axis, we have plotted sin square n alpha upon sin square alpha, while on the horizontal axis, it is the value of theta which is being varied, or value of sin theta which is being varied. Now, you see that as you increase the number of slits, new features appear. Okay. For smaller number of slits, you see only big principal maxima peaks, it is going down to 0, and then again the next peak appear. While for larger number of slits, apart from the usual central maxima which we predicted to appear at lambda by a or 2 lambda by a and so on. Several subsidiary maxima also appear between them and several minima also appear. Now, if you plot the whole function, which is your I theta by I naught, then what you see is that the pattern which you see here in the first plot, it slowly decays down as you increase sin theta. Now, why is it so? This is what exactly is mentioned here. Now, you see that there is some pattern which is given by sin n alpha by alpha whole square, and this is a rapidly varying function. This function is being modulated by single slit diffraction pattern. Okay. Now, this is the rapidly varying function which is sin square n alpha upon sin square alpha, and if you multiply this function by sin beta by beta whole square, which is a slowly varying function, it means that that function will now envelop it, that function will now modulate it, and this function is plotted here. This is the diffraction, single slit diffraction, sin square beta by beta square. This single slit diffraction now envelop the underlying function which is sin n alpha upon sin alpha whole square. Therefore, the overall pattern would look like this. This is with the continuous line, the overall pattern is drawn, where at sin theta is equal to 0 you see highest peak, and as you move outward, this principal maxima intensity or irradiance, it decays down due to the single slit envelope or single slit modulation. Now, you see that you can compare this with a diffraction grating also, because in grating we have multiple slits. Okay. The same analysis also hold here. We will talk more about grating in next module, but you can now start having a comparison. You can see that it is this study is basically a diffraction grating study, yeah, because there are so many opaque and transparent portion in a aperture, okay, and which clearly mimics diffraction grating. Okay. Now, with this I end this lecture. See you in the next class.